Good morning, students. Let us start the class. We had seen this example yesterday where we saw that this particular syndrome 1100 is not present in this particular H transpose matrix. So, the receiver has computed the syndrome, but the syndrome, as it is not present in the H transpose matrix, the receiver is unable to find out in which position the error is. So this means that the receiver is able to detect the error because syndrome is non-zero. So it is able to detect the error, but it is unable to correct the error because the position of the error cannot be found out. This is called error detecting ability and error correcting inability. Yesterday we had seen the Hamming weight and the Hamming distance, where we had two theorems where the error detecting ability can be larger, error correcting ability can be lesser, which means the error detecting ability can be 3, whereas the error correcting ability can be either 2 or 1 also. What does it mean? It means that it can obtain all these syndromes one after the other, but if the syndromes are not present in the transpose of the Hamming matrix, it will be unable to correct the error because it does not know in which position the error is. So coming back to this particular example, the syndrome vector is not present in H transpose. This means that the number of errors in the received code word is more than 1, and hence the error is detected but cannot be corrected. Therefore, the receiver has to use the ARQ method for such errors. Whichever syndrome vector is available at the receiver, and if it is not present in the transpose of the Hamming matrix, then the receiver will ask the transmitter to send the data once again only for those received vectors. Please understand this. Only for those received vectors for which it is unable to correct the error, it is going to ask the transmitter to send it back. Now, the receiver has to use the ARQ method for such errors, which means to say that the receiver has to request the transmitter to send the code vector once again only when it is unable to find the position of the error. So there will be a slight delay which is being incurred because the transmitter has to send the code vector back and the receiver has to detect it once again. Until then, there will be slight delay there. But to some extent, this delay can be tolerated because the ARQ method is being utilized only for those errors which the receiver is unable to correct. And that probability also will be lesser. As you can see in H transpose, we have 1, 2, 3, 4, 5, 6, 7, 8 syndromes. Now, the syndrome which is computed for the received vector, if it is within these 8 syndromes, then error detection is also possible, error correction is also possible. But when the syndrome is not present here, then the detection is possible, correction is not possible. Only in such cases, ARQ method is going to be utilized. Now, what may be the solution for this? The solution is to have a bigger parity matrix, so that we will have more number of syndrome vectors. That is one solution. If at all the receiver is able to compute all the syndromes, then it can correct all the errors. For example, now this is a 4-bit syndrome. 4-bit syndrome means we should have 16 vectors here. Now leaving out the 0, 0, 0, 0, we should have at least 15 vectors here in the H transposed. If all the 15 are present, then it is possible to detect all the errors and correct all the errors. But that will require additional amount of resources. We will have to have larger number of matrix computations. That is where we make a compromise. We use a combination of the normal method as well as the ARQ method so as to detect as well as correct the errors. Otherwise, we will have to have larger amount of resources reserved where we will have all the syndromes to be listed in the H transposed matrix. That is the idea here. Now let me proceed for the next part of the problem. The next part of the problem wanted us to write the encoder circuit. Now the encoder circuit can be directly written using the given expressions. We already have these expressions, right? Now we have these expressions. C5 equals D1 plus D2 plus D4. C6 equals D1 plus D2 plus D3. Like that for C7 and C8. Now using these expressions, we can directly write the encoder circuit. You can see C1 is D1, C2 is D2, that is already known. Now C5 you can see that is D1 plus D2 plus D4. You can see the connections here. I have written the connections accordingly. Imagine that plus corresponds to modulo 2 addition only, it is XOR addition only. Similarly, C6 is D2 and then D1 and then D3. This is in accordance with the given expressions. Similarly for C7 and C8. Now we have to write the syndrome calculation circuit. We can write the syndrome calculation circuit from the H transpose directly as S1 equals R1 plus R2 plus R4 plus R5. Let me show you H transpose. You can see here the first column corresponds to S1, R1 plus R2 plus R4 plus R5. Similarly, syndrome 2, the second bit of the syndrome, it is not syndrome 2, the second bit of the syndrome. Syndrome is now 4 bits. I should say, not the second bit, the first bit whichever I mentioned was MSB, I should tell the second bit from the left hand side. That is R1 plus R2 plus R3 plus leave out R4, leave out R5, it is R6. R1 plus R2 plus R3 plus R6. So you can see here S2 is R1 plus R2 plus R3 plus R6. Similarly, for the third bit and the fourth bit in the syndrome, we can write R1 plus R3 plus R4 plus R7 and S4 equals R2 plus R3 plus R4 plus R8. In this way, we can write the hardware for the syndrome calculation circuit in accordance with these equations. You can see that S1 is R1 plus R2 plus R4 plus R5. So that S1 is, you have R1 here, then you have R2 coming here, then you have R4 coming here, then you have R5 coming here. That way I have written the respective bits from the received code vector as inputs to this particular XOR gate, and the output of that XOR gate is S1. Similarly, later on you can verify the connections for S2, S3 and S4 in accordance with these three equations. So this was the exercise which we started yesterday. Let me continue the theoretical discussion of this module now. We have till now discussed the single error correcting Hamming codes. Let us go into a little more detail in the single error correcting Hamming codes. We know that H transposed is the parity matrix at the top and identity matrix at the bottom, and the order of the identity matrix is n minus k, and totally the order of the H transposed is n cross n minus k. Now as there are n minus k columns in H transposed, there can be 2 power n minus k distinct combinations of the rows, right? We have n minus k columns. As we have n minus k columns, each column corresponds to a bit in the syndrome. So naturally, we can have 2 power n minus k distinct combinations because we are using the binary alphabet. Now out of these rows, we have to discard the row of all zeros, because all zeros means no error. Syndrome vector, when we get 0, that means no error. Actually, such all zeros row need not be there in H transposed, because it is useless for us in H transposed. The reason is, if in H transposed, if you have all zeros in one row, then as there will be no errors, it is simply occupying the space in that particular matrix, which is of no use. So we have to discard the row of all zeros, as it represents the syndrome of no error. Hence we are left with 2 power n minus k minus 1 rows. Now there are n rows in H transposed, right? And the condition for all of them to be distinct, all these n rows in the H transposed should be having distinct syndrome vectors. So in that case, n has to be less than or equal to 2 power n minus k minus 1. As we have seen, we have 2 power n minus k minus 1 total number of rows. So naturally, this n must be less than or equal to 2 power n minus k minus 1. Now, what is this equation now? This equation indicates that we have a binding condition for the Hamming matrix also, Hamming transposed also, right? Hamming transposed is obtained from the Hamming matrix. Now, in the Hamming transposed, we have n rows, they must be at least equal to 2 power n minus k minus 1, or they can be less also. As we have seen in the previous example, we don't have all the syndrome vectors in the H transposed. So in that case, n is less than 2 power n minus k minus 1. The number of rows in the Hamming transposed is actually less than the total number of rows that are possible, excluding the rows having all zeros. So we can write it this way: n is less than or equal to 2 power n minus k minus 1. Now, let us expand this. Bringing this 1 to this side, n plus 1 is less than or equal to 2 power n minus k. Now, there is this 2 power n minus k. Let us take a log to the base 2. Then, Lg of n plus 1 is less than or equal to n minus k. Or, k has to be less than or equal to n minus Lg of n plus 1. Now, look at this equation. We have a expression here where k has to be less than or equal to n minus Lg of n plus 1. Now, what does this equation indicate? Till now, we did not bother much about the relationship between k and n, where n is the number of bits in the code vector and k is the number of bits in the data vector. We have been using arbitrarily a particular parity matrix, and we have been using it till now. In all our examples, we did not really bother about the number of bits to be present as check bits. Now look at this equation. This equation indicates that there is a distinct relationship between the data bits and the code bits. And this indicates about the error detecting and correcting abilities of the receiver as well. There must be a distinct relationship between k and n. That is what is indicated here. So let me elaborate further. Now these equations become useful in deciding upon the parity matrix P. As I told you, till now we did not worry much about the number of bits should be present as check bits. We have been arbitrarily taking it as 3 and 3, totally 6. We had codes like 6, 3. The n used to be taken as 6, and number of data bits was also 3, number of check bits was also 3. But we did not discuss at that time about the relationship between k and n. But now these equations become useful in deciding upon the parity matrix. Okay, let me proceed now. Let me rotate this page. Now, let us have one more exercise. Design a n comma k Hamming code with message length of 4 bits. Now given is k is 4. We have to decide upon n now. And why is it called as Hamming code? Because we have discussed the Hamming weight and Hamming distance. We have discussed about the limitations of error detection and the error corrections. So now we have to design a Hamming code. Given k is 4, code length is n has to be less than or equal to 2 power n minus 4 minus 1. Now for n equals 5, look at this. 5 should be less than or equal to 2 minus 1. That is not being satisfied if we consider n as 5. K is 4, we can directly go to n as 5, adding only one check bit. But adding one check bit is not satisfying our condition. Now let us go to n equals 6. When you go to n is equal 6 also, 6 is not less than or equal to 4 minus 1. So we cannot have a Hamming code with the k equals 4 and n equals 6. We cannot accommodate only 2 check bits. Now for n equals 7, 7 is less than or equal to 8 minus 1. Now that is satisfied. 7 is equal to 7. That is satisfied. Means for a 4-bit data vector, we can have a 3-bit check bit. Totally we can have the code vector of 7 bits. So n equals 7 is possible. N can be 8 also, 9 also, 10 also. When n is still larger, we will have still larger number of syndromes. So this is a Hamming code now. N has to be at least equal to 7 for k equals 4. As I mentioned, we did not worry much about this particular relationship till now, because the intention there was to understand the procedures only at that time. Now we are discussing all these intrinsic complications in choosing the number of check bits or in deciding upon the contents of the parity matrix. So now n equals 7, therefore H transposed is now P at the top and I n minus k at the bottom, that is P and I3. Total dimension of this H transpose is 7 cross 3. Right? Because n is 7 and number of check bits is 3. So it is n cross n minus k. That is 7 cross 3. Now let us see what is going to happen here. The parity matrix P should not contain the combination 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1. At the top we have this parity matrix. It should not contain 0, 0, 0, obviously, because it is of no value. It should not contain 1, 0, 0, 0, 1, 0, 0, 0, 1 also, because they are part of identity matrix, which is just below. As 0, 0, 0 corresponds to null syndrome and other combinations are part of I3. Now hence out of these total 8 combinations, we are left with what? We are left with 0, 1, 1, 1, 0, 1, 1, 1, 0, 1, 1, 1. See, right from 0, 0, 0 till 1, 1, 1, we have totally 2 power 3 equals 8 combinations. Out of the 8 combinations, we have to discard 4 combinations just like that, because one is a null syndrome, other 3 are part of the identity matrix. We are left with only 4. Now this is again 7 cross 3, means the bottom 3 rows are 1, 0, 0, 0, 1, 0, 0, 0, 1. Isn't it? The bottom 3 rows are 1, 0, 0, 0, 1, 0, 0, 0, 1. That is the identity matrix. At the top we are supposed to have 4 rows. Now the 4 rows can be 0, 1, 1, 1, 0, 1, 1, 1, 0, 1, 1, 1. Hence we can have the parity matrix now as 0, 1, 1, 1, 0, 1, 1, 1, 0, 1, 1, 1. This way we can decide upon the parity matrix. Students, please understand, in all our previous examples, parity matrix was already given and we have been working out the exercises. But the real point is, even the parity matrix has to be decided by the designers. It will not be given as such. Only the requirements will be given, that this is the number of data bits that is going to be coming out of the source encoder. That is given. The channel encoder's number of bits that are coming out has to be decided, as we decided that here n equals 7. In the same way, even the parity matrix also has to be decided by the designer. That is the concept which we are discussing now. So, to proceed, now we can write the Hamming matrix. That H is P transposed along with I n minus k. Now, P transposed we can write. That is 0, 1, 1, 1, 1, 0, 1, 1, 1, 1, 0, 1. You can see here 0, 1, 1, 1, 1, 0, 1, 1, 1, 1, 0, 1. That is P transposed. Then we can write the identity matrix. That is 1, 0, 0, 0, 1, 0, 0, 0, 1. So, this is the Hamming matrix now, which is going to be utilized at the receiver for error detection and correction. Let me rotate this page once again. Okay, so in the previous page we had seen that Hamming matrix. There is a question. Let me see what is the question. Should the parity matrix be always in order? We can shuffle the rows. You can shuffle the rows. It is not necessary that the parity matrix has to be having whatever the bit combinations we had. We need not arrange in the same manner. We can shuffle the rows. That freedom we have. When you shuffle them, what happens? The syndromes which are going to be generated will be in different rows. That's all. Actually, in the parity matrix, there need not be such order at all. The more we randomize it, the better, because noise is basically random. When we randomize it, it is still the better, because noise is always random. Noise will never be systematic. So, there is no point in having a parity matrix also which is systematic. Okay, that is the answer. Now, let me proceed. Now, for this H we obtain, we can write the generator matrix at the transmitter, that is Ik along with the P. Now, this Ik identity matrix is of the size 4 cross 4. So, 1 0 0 0, 0 1 0 0, 0 0 1 0, 0 0 0 1. Then the parity matrix we write as it is 0 1 1, 1 0 1, 1 1 0, 1 1 1. That way we have a generator matrix now. Now, using this generator matrix, we can now find out the code vectors. I have already written all the code vectors for all the input bits. Our K was 4, right? And our N was 7. So, for the very first 0 0 0 0, obviously the code vector is 0 0 0 0 0 0 0. Later on, I have written from 0 0 0 1 till 1 1 1 1, I have written all the code vectors. You can see the Hamming weight here. The Hamming weight here is, for each of the Hamming weights there is a value written, but the minimum Hamming weight is 3. When the minimum Hamming weight is 3, it simply means that this particular scheme of n comma k, or this particular parity matrix, can detect 2 errors. Here d min is 3. The minimum Hamming weight is 3. So, d minimum is 3. You remember that theorem? Hamming weight and Hamming distance are strangely related. When they are related, here, even though we are telling it is a d minimum, the minimum Hamming distance, that is nothing but minimum Hamming weight, that is 3. So, now the code can detect 3 minus 1, 2 errors, and the code can correct that small t equals d min minus 1 by 2. That is 3 minus 1 is 2, 2 by 2 is 1 error. It can detect 2 errors, it can correct one error. That means as we are using a parity matrix of 3 bits and as our data bits are 4, now in the Hamming transposed, you will not get all the syndromes that can be obtained at the receiver. You understand the point? The data is 4 bits, whereas the parity is having only 3 bits. We want a syndrome which has to be 4 bits, but we will not get it that way. So in that case, H transpose will not have all the possible syndrome vectors. And that's what I had told you in the beginning also earlier, that it can detect 2 errors, it can correct only 1 error. Let us see what is the efficiency of this particular code. The efficiency is defined by K by N. K is 4, N is 7, so efficiency is 57.14%. Now if K is 64, then N equals 71, then efficiency can be 64 by 71. So what does this indicate? When the block size increases, the code efficiency also increases. Look at this. Between 64 and 71, the difference is only 7 bits. N is 71, K is 64. But you can see the efficiency is much larger. When the block size is lesser, efficiency is also lesser. So this means that the total block size is more number of bits, then it is efficient. When there are more number of bits, the probability of error also reduces there, right? So hence when the block size increases, the code efficiency also increases. Let us see one more exercise now. The syndrome vectors for a linear block code are given in this manner. That means now H transpose is given. S1 equals R1 plus R3 plus R4 plus R5. S2 equals R1 plus R2 plus R3 plus R6. And S3 equals R2 plus R3 plus R4 plus R7. Now the question asked is, find the code vectors and demin, correct the received vectors 1011011 and 01100000. Prove that G into H transpose is 0 for this exercise. Yesterday I had asked you that you can try out that particular proof of CH transpose equals 0 on your own by actually substituting those vectors. Now in this exercise we are going to have that exercise. Okay, find the code vectors for the given syndrome vectors and correct the received vectors also. Now the received vector is 1 cross 7. Isn't it? We can see this. The received vector is 1 cross 7. That means here N given is 7. Now there are only 3 syndrome bits given. Okay, the syndrome bits given is 3, S1, S2, S3. And the order of the syndrome is now 1 cross 3. So obviously N minus K is 3. Please understand this. The received vector is 7 bits. Syndrome is 3 bits. So the order of the syndrome is 1 cross 3. Order of the received vector is 1 cross 7. That means N equals 7 and N minus K is 3 because the order of the syndrome itself is what? 1 cross N minus K, right? So N minus K is 3. So K is how much? K is 4. It is a 7 cross 4 scheme. So K is 7 minus 3 by 4. Now from the given syndrome properties, H transpose can be written by using these equations for S1, S2 and S3. H transpose can be written and we have written it here. H transpose is written this way. You can see this. S1 is R1 plus R3 plus R4 plus R5. R1 plus R3 plus R4 plus R5. That way S1 is written. Similarly, S2 and S3 are written. So now this is H transpose. Parity matrix at the top, identity matrix at the bottom. Actually, you are getting this identity matrix automatically by the given equations. Actually, given equations have to match in this manner. Now, at the top, you have the parity matrix 1 1 0, 0 1 1, 1 1 1, 1 0 1. Right? This is the parity matrix. We can write H now, which will contain again the transpose of the parity. That is 1 0 1 1, 1 1 1 0, 0 1 1 1. You can see here 1 0 1 1, 1 1 1 0, 0 1 1 1. So the parity matrix is transposed here. Then we have another identity matrix, that is 1 0 0, 0 1 0, 0 0 1. We have this Hamming matrix now. Now we can write the generator matrix because we have already the parity matrix. Let me annotate. See, till here it is parity matrix, below which here identity matrix. So transposing this parity matrix, we have obtained this Hamming matrix. This Hamming matrix. Hamming matrix contains the transpose of the parity along with the identity matrix. Now generator matrix is identity matrix of 4 cross 4, then the parity matrix. So you can see here the generator matrix is, identity matrix is written here, and the same parity matrix 1 1 0, 0 1 1, 1 1 1, 1 0 1 is written here. So now we have everything, right? We have the generator matrix, we have the Hamming matrix. Using these, we can actually find out the code vectors, we can actually perform the error detection and correction also. So now, he has asked us to prove GH transpose must be 0. Now look at this, GH transposed. G is there, H is there. G is I4 and P, 4 cross 7. H transposed is 7 cross 3. So naturally, we should get something wrong. It is not 4 cross 7. I have written wrongly. What is wrong here? Something wrong. G is I4 and P. G is 4 cross 7. And H transposed is 7 cross 3. That is correct, 7 cross 3. So we should get 4 cross 3. Yeah, that is what is wrong. I must have written one more row having 0, 0, 0. That I have not written. Now this is wrong. This is wrong. It is not 3 cross 3. It has to be 4 cross 3. I should have, let me change the color here. I should have one more row having 0, 0, 0. Now this should be 4 cross 3. Right? It should be 4 cross 3. Which one is the eraser? This one is the eraser. Let me erase this. Yeah. Okay. So this is now 4 cross 3. You can actually multiply. We had proved it earlier that the corresponding element is going to be XORed with itself. We will find out. So we have to multiply G with H transpose. So this one, I have to stop annotating now. This particular one and this particular one, 1 into 1, then 0, 0, 0, then again this particular one, see this 4 zeros, then this particular one, this particular one, this particular one, then again this is 0, this is 0. So we will get 1 XOR 1. We will get that 0 only. You can see this 1011 is here, 1011 is here, then 100 is here in H transpose. Here, whatever is corresponding to this particular one, and that one will somehow come in G also, right? Because G is what? I4 with P. H is what? P transpose with I3. So correspondingly, the P transpose is present here and the P is present here, right, in H. So when you multiply G and H transposed, you are actually multiplying or performing XOR operation with the same element again. That is how you can actually work out all these things. You will get all types of zeros. 4 rows with 3 columns, everything is 0. So that way GH transpose is proved to be 0. Now he has asked us to find out the code vectors. Code vectors can be easily found out by simply writing C equals D into G, because we have a generator matrix. Using that, I have already written all the code vectors here, right from 0001, 101 till 1111, 111. Here also you can see the dmin is 3. So here dmin is 3 and the error correcting ability is 3 minus 1 by 2 equals 1. When R equals 1011011, we will find out the syndrome as 111. He has asked us to find out the syndrome, right? So it is 111. This syndrome is in the third row of H transposed. That 111 is in the third row. That means the third bit is under error. Third bit is under error. So the corrected vector is 1001011. Now when R is 0110000, syndrome is 100. That 100 is present in the fifth row of H transposed. That means the fifth bit is under error. The fifth bit here is 0. It has to be flipped into 1. So the corrected R is 0110100. This is how for both of the received vectors the correction is also done. So this is the exercise which we completed now. Let us have a general theoretical discussion about the properties of syndrome. The first property, for all the single error patterns, the syndromes generated are unique. They have to be unique. We cannot have two syndrome vectors having the same value, as I have told you. Otherwise, it will lead to ambiguity. We will not be able to locate the position of the error. So for all the single error patterns, the syndromes generated are unique. The next property is the syndromes generated for double error patterns are different from those of single error patterns, which means, let us say in a given received vector, if there are 2-bit errors, let us say we want to detect as well as correct 2-bit errors. Now the syndromes generated for those double error patterns will be different than those of the single error patterns. But we are not discussing the double error, triple error patterns or double error, triple error correcting codes in our course here, because it is going to become too much complicated. It is not complicated, procedure is same, but it will be too much of competitive, I should say. If at all we have to manually do all those calculations or computations, it will take us more time, because the size of the matrices will be increasing. That is why it is not going to be covered in our course. But in the real life application, there are these double error corrections, triple error corrections, double error patterns, triple error patterns, they are all there. It is very easy to write a MATLAB code and to implement it, or it is very easy to write a Verilog code and to then synthesize and obtain the hardware also. That way it is easier than to manually proceed with such computations. That is why in our curriculum we don't have it. We have been discussing only single bit error correction and detection till now, only for the sake of understanding, where we can manually do all the calculations. So the second property is the syndrome generated for double error patterns are different from those of single error patterns. Now the third property is, depending upon the length of the code, the syndromes of double error patterns may not be unique. Look at this. Depending upon the length of the code, the syndromes of the double error patterns may not be unique, which means to say that the same syndrome can be generated for different code vectors received. That is the complication we will have. That is when we can have error detectability more, but error correctability lesser. We may get the same syndrome that can be generated for different code vectors received. So what is the solution now? We have been using only XOR algorithm till now because it was very simple for us. We may not be able to use XOR algorithm everywhere there. If at all we keep on using XOR only, then we will have to live with this particular problem. Same syndrome can be generated for two different code vectors received. That is also possible. Now lastly, if the syndromes are not unique, then the error is detected, but it cannot be corrected. Now what is the difference between the third one and the fourth one? The third one says that same syndrome can be generated for two different code vectors that are received. Okay, it is for this double error patterns because we are going for this XOR algorithm. If we don't want to have that, then we'll have to have different types of algorithms or different types of relationship between n and k as well. Okay. Now, if the syndromes are not unique, then the error is detected, but it cannot be corrected. This we have seen already. These are the four properties of syndrome. In the next class, we will see one concept called as Hamming bound. Okay, today it is already time up. I am going to end the class now. See you in the next class. Until then, take care and goodbye.